I think it's time now that we move to our first keynote speaker. So I'd like to introduce Vivian Kendon from University of Durham in UK. So she's a professor in the physics, and she has been involved in quantum computing for at least 20 years with an interest for application and also focus on the computing limit. So today our talk is about quantum computing, prospects and challenges. And I think we'll learn what this machine can do and probably how we can maybe combine them with more classical machine. So if you have questions during the talk, please use the chat. So in the platform, you have a chat. You should just put your name on it and ask your question there. And at the end of the talk, we'll come back to this and I will read this question to Vivian. So Vivian, the floor is yours. Thank you very much.
Thank you very much. Hopefully you can all hear me. Let me get my screen shared with the right one of these things. So that's the one we need. There we go. That should be my opening slide. Good. So I'm really honored to give the opening plenary at this wonderful event. And I've thoroughly enjoyed hearing about Geneva, like everybody else. I'm very sad not to be there in person, but very happy this is going ahead nonetheless. So I'm going to try to tell you something about the current state of quantum computing. Right now, there's a huge amount of hype. So if you look for some of the latest headlines, you'll easily find choice ones like this leaping out at you. There are lots of wild claims and promises, talks of revolutions, of paradigm shifts, and there's huge venture capital investment. Now, one thing you need to remember is venture capitalists will expect more than 9 out of 10 of their investments to fail. That's how they operate. Now, I don't expect that many to fail in quantum computing, but it's something to put the lid on the claims. So in this talk, I'm going to try to tell you about quantum computing without the hype and give you some insight on where the real promise might come from. But there is one thing to take away from the hype currently. All the promises, of course, are for the venture capitalists. But let's see what we can actually do with the quantum computers that have been built so far. So Google and IBM, for example, have quantum chips with about 60 or so qubits. They're noisy, they're imperfect, even when cooled to very low temperatures. And if they run a particular random sampling task, it's not a useful task, it was chosen to be hard for a classical computer. What they found was that you need near exascale classical HPC to verify the output of the quantum 60 or so noisy imperfect qubits. Of course, there's lots of caveats and arguments about this, but there is a take-home message from under the hype. That potential is real, even for the early hardware. But if, and there's a very big if here, we can use it for something we actually want to compute. So it's time to think seriously about how to use a quantum computer as they develop the next improvements on them, because around the corner is something that might actually make a difference to the computing power we have available. So here's an overview of my talk. The hype, I'm done with hype. I'll give some proper motivation and context. I'll try to give you insight at the really basic level. What is quantum computing? How it works, what it might be useful for, some sense that there's still a lot of different hardware and models, even above the hardware level of quantum computing, and some near-term outlook. So, context, motivation. There was a time when no talk about the future of computing would be complete without a Moore's law graph. And then suddenly they went away. So what happened? So I went looking, this is a good few years ago now, for the next iteration of the Moore's law graph, and I couldn't find it. So I plotted my own. This is just for Intel chips and just up to 2012, and it's their own data from their own website. So this is an earlier version of the graph that was actually off their website up to the year 2000, and it goes up to that point there. It's this line here. So what you would most often see is the number of transistors on the chip. The most interesting line, of course, is the speed, which is the blue line here in hertz. And this is the feature size in meters down here. So that's 11, and then we're still going down to 7 nanometers here. So the feature size is still dropping. We're not so much packing more transistors on the chip, and the speed has leveled off. But I didn't plot any more after this up here, because what you find is there's hundreds of chips now. What they've done, instead of just making a straight up faster chip, they've diversified. Now you can find a chip, whatever your application, they've got a chip for you. You want a toaster, a mobile phone, something that will stand up to life on Mars, they'll sell you the right chip for it. So there's something happening to classical computing anyway at this time that makes it ripe to put new kinds of computing in the mix. And beyond silicon, well, there's quantum, but there's also a whole lot of crazier things that people have been playing around with for a good decade or two, just to learn more about what computing is and what the possibilities are. But the thing to note about these different types we've got here, they almost all have a conventional computer as a control layer somewhere in there. Maybe not the slime molds, but I'm not going to talk anymore about them. But this, you can see here, it's like a computer chip, and it's going to be plugged into a circuit board and controlled by a classical computer. So hybrid computers are the norm. In practice, we have co-processors, and we have had for decades. GPUs came along a long time ago now, first of all to do dedicated tasks like graphics, but then they were immediately co-opted as a faster method of computing, provided you could figure out how to program it. We now have any well-appointed high-performance computing facility is going to have a range of different things besides standard silicon chips for you to put your programs onto. And the unconventional, here we are, quantum, NMR, reservoir, slime mold. There's a much bigger list of things here that people are playing around with. However, theory tends to be single paradigm. Classical, we have the Turing machine as a theory, which is not a lot like the computers we use in practice. Analog, we've got Shannon's general purpose analog computer model. Quantum, now quantum has a whole bunch of models. I've put a lot of letters here, but and that there are at least, that's quantum Turing machine, continuous variable, measurement-based quantum computing, quantum walks, adiabatic quantum computing, and there are more. So it hasn't settled into one model, although most of them are equivalent. There are also other things like linear optics that are somewhere between classical and quantum, although we don't have strong use cases for them yet. So bosons, computing with bosons, which are indistinguishable particles, I tried to think what the classical equivalent of that would be. It would be a little bit like saying you had to try and use a computer where you didn't know whether the operations were going to be big endian or little endian for each one that you did. So you'd have to do something that was symmetric in the order of the qubits, of the bits that you're using. You couldn't assume that the bit order was preserved, which would be very weird, but that's what you can build a computational model like this with quantum particles that does something more powerful than classical. So if we want to understand quantum computing, let's try to do it in the single paradigm setting first. But let's step back even a little further and say, what are we doing when we compute? So we have our user here, and the user is important, with a problem that gets encoded into a computation, put on some computational hardware. You run the program, run the computation, and you end up with some output from it. Computations have outputs. You read that and you reverse this process up here, you decode it and relate it back to your original problem to get your result. So this is a slide from my public outreach talk, but actually it's based on a whole sequence of articles. This is the first one, looking at what you can deduce about computation in this kind of setting. Particularly, the user is important, as any of you will well know. So quantum computing. So here is that same picture, but I flattened it out. So follow that line like this. And here we go along here. Input, encode. Now that funny bracket thing, that says we've got a quantum state at that point. So just bear with me on the notation. And that thing is a unitary operation, which is what you do, how you model the time evolution of a quantum system. So you get a new quantum state here, you measure it, decode, and you get your result. So that's satisfying because it looks very much like the picture I just put up there of what computing is and what it does. We've just used a different type of physical system to get from our input to our result. So what is U? So U is unitary evolution. More generally, it's open system or environment, but that's not, we don't need to worry about that for purposes of this talk. So we can make it up of a gate sequence, or we could have a continuous time evolution. We engineer a Hamiltonian, and if you don't know what a Hamiltonian is, think of it as an energy function, something that can tell you how much energy is in the system. And the output state then is the exponential of the time integral of this time-dependent Hamiltonian. And that funny T is telling us that we've got to do this in the right order because it's matrices, and matrices don't commute, so you have to line them up in the right order when you use them. So this model covers most of quantum information processing, including communications, where what your aim is to make the input and the result match, despite having some interruptions and noise and so on along the way. And I just want to note, encode has some arbitrary choices in it. We have a choice whether to use some sort of physical spin down as our zero or the spin up as our zero. It makes no difference provided these are done consistently. And that's another feature of computing. There's some arbitrariness in the encoding in general, not just for quantum. So quantum information processing. Quantum computing and communications are built on the idea that quantum logic allows greater efficiency than classical logic. So classical, we have bits. We have, in quantum case, we have qubits. Here's the 0 and the 1 in these funny brackets. And alpha and beta are complex numbers. And so the relationship between this superposition we've got here is called the coherence. There's a phase angle here, which is given by this complex number. In classical, we have yes, no, we have binary decisions. Here, clearly, we can have yes and no in superposition. And we have heads, usually we add random numbers to classical. In quantum, you have them built in. Measurement outcomes are random if done in the right way. So intrinsically, if quantum mechanics holds, then randomness is built in to quantum computing. So quantum logic is different from classical logic. It stands to reason it gives you different computation from classical. The question is, how different is it? And so we can ask about computability or about complexity. So what can we compute and how efficiently can it be computed? So quantum computability is the same as classical. You can use a classical system to simulate a quantum one. It just won't be very efficient. Complexity, however, can differ. Some problems can be computed more efficiently. So now it begs the question, what's our definition of efficient? So a quantum advantage, then, is what we're looking for, how to translate the logic into better computing devices. And it depends on your definition of efficiency. So in theory, you want what theorists call efficient is some sort of polynomial scaling with system size. In practice, what we call efficient is something that produces answers on human timescales. There doesn't appear to be a lot of overlap in those two definitions, and I suspect most of the audience here is more interested in the in practice one. I certainly am too. I'm interested in actually applying quantum computers, but sometimes it's good to understand the theory to know what at least predicts is possible. So roughly speaking, you get a quadratic speed up, so you get something that improves the polynomial if you exploit that quantum coherence, the interference effects you get from here. And if you want an exponential speed up, you have to exploit the parallelism in quantum superposition. But comparisons of real physical devices are not the same as mathematical theories. And complexity theory will tell you what is possible in a sort of scaling manner, but it won't tell you what whether it's useful in practice. For that, you're going to need to try and include a lot more factors. So let's break down a little more how quantum computing might work. We'll take the most standard model, which is the gate model or circuit model, which is very similar to the classical model of computing. We have qubits instead of bits. They're two-state quantum systems, and we need to make them out of something. You can take electrons, and instead of using the charge to make a plus or minus charge, say for a classical bit, you can use a property it's got that's called spin. So if you've heard of spintronics, that's the property that you're trying to use, but of individual electrons rather than a whole stream of them. You can use photon polarization. So photons are single quanta of light, and the polarization works just like you're familiar with in day-to-day with Polaroid sunglasses. It's got two orthogonal directions, and you can use that to make your qubits out of. We also localize them so they're distinguishable, and we don't have to worry about the Fermi or Bose statistics that quantum systems come with when they're not distinguishable. We choose properties of our quantum system to be our 0 and our 1. It comes with superpositions automatically. That's quantum mechanics. And here's that model again from a few slides ago. Input, encode, we're still classical. Set up our quantum state with its input, run our computation, get the output, classical again, we decode and get our result. So how are we going to apply U? So U is in a sense the program. It could be any unitary, but our program needs to be efficient. It needs an efficient description. And for n qubits, U is a 2 to the n by 2 to the n matrix. So an efficient program means we need a sparse matrix that only has polynomially many non-zero entries here. We can decompose U into smaller operations applied to a few qubits at a time. And this is an important result. Just like classical, for quantum, we can get a universal gate set. So one entangling 2-qubit gate and a few single qubit gates, and you can construct any unitary. And we know how to do this efficiently to go from the unitary to the sequence of gates. Which universal gate set to choose? We've got choices here, and that's a question that depends on the physical system and the error correction requirements. So you have some flexibility to match it to the physical system that you're building. Quantum superpositions now. So consider 3 qubits. Here they are, all zeros, or flip one, so you've got 0, 0, 1. So what I'm putting here looks completely classical. I'm just dealing with basis states. And of course, it represents 8 numbers labeled from 0 to 7 here. So suppose we want to compute a function for 8 different values of x, these 8 values. Classically, we run the program 8 times, once for each value of x. But what if we could put all 8 values in at once? Quantum mechanics lets us do this in superposition. So we can make a state that looks something like this. It needs a normalization factor, but that's just convention. Of course, there's no free lunch. You get a superposition of all 8 answers out of that, which may not be useful at all. You need a way to select one, find out which x it corresponded to, and then you might have a quantum advantage. So you're going to need some very smart quantum algorithms. Useful quantum computing needs quantum algorithms, and they need to be pretty creative about how you're going to get classical answers out of quantum superpositions like this. So I'll give you the example, Shor's algorithm for factoring numbers. And this is my 1-slide version of Shor's algorithm. You either do a whole talk on it, or you do it at this level of detail. So the threat is that a large enough quantum computer will break this. And on the next slide, I'll give you some numbers for how large. Will break the crypto schemes that rely on factoring being hard for large numbers. So our problem is this. We want to find a factor of a number n that's given to be a product of 2 primes, p and q. The algorithm, you first choose a co-prime number a, so q, co-prime to n. So it's not got either p or q as a factor. And it's actually efficient to test this using classically using Euclid's algorithm. And obviously, if it's not co-prime, you're done. You've just found a factor. So you feed this into some classical number theory, and out comes a recipe for preparing a complicated superposition quantum state, which involves a whole bunch of quantum gates here. Then you do a quantum Fourier transform. And then you measure part of this register, do some more classical number theory, and you get a factor with high probability, not for certain, but you can repeat it a few times if you're not successful. Try a different A if that one didn't work very well. So what's going on here is the hard bit is to find periodicity R of, excuse me, of X, which is our, to the power A mod n, for x of between 0 and n. So x is our superposition of all possible states, which we put in here, like we had here. So this is our x, but larger now. And to find periodicity, Fourier transforms are good at this, right? That's how you find periodic things. That's what a Fourier transform does. It gives you spikes telling you what the different periodicities you've got in your function. And it turns out that the quantum Fourier transform in this setting on this superposition state is exponentially faster than the classical Fourier transform. You then take a to the r over 2 plus or minus 1, and it gives a factor of n with high probability, but that's classical number theory. Okay, so that's what we're trying to do. How good is it? Well, if we want to beat classical, the best classical is still, I believe, 232 digits, so RSA 768. So 768-bit numbers. Shor's algorithm for n bits needs 2 n qubits in the QFT register, 5 n qubits for modular exponentiation, so you get 7 n total. Now, it is possible to use less than this, but it's just a constant factor, so it doesn't make a lot of difference here. So for 768 bits, we need 5,376 logical qubits. So pretty much a couple of orders of magnitude more than we've got currently, and remember those were noisy. However, they were noisy. We need error correction if we're going to do this efficiently. How much depends on the error rates. For low error rates, maybe 20 to 200 physical qubits per logical qubit. The high error rates may be 10 to the 5. So we may need teraqubit quantum computers before we're going to break factoring. The scaling favors quantum, but the crossover point is high. So the current hardware factors 35, i.e. a 6-bit number. However, there's another algorithm that may challenge sooner. So relatively recently, this is 2018, D-Wave, which is quantum annealing hardware, and I'll tell you a little bit about this in a couple of slides, using a different algorithm, which has a scaling of n² qubits, and their current hardware will do 18-bit numbers. So that's 3 times the 6 bits here and beginning to get into more interesting territory. You'd need to be about 1,500 times larger for RSA 768, but there's a huge uncertainty in how to embed it in the hardware. So you need 147,000 qubits. That's the n² versus the n7n here. But the overhead from the point of view of the error correction is not necessarily as high. Now, we think currently they can do more than this, but they're not talking about it as much because the US National Security Agency is funding the work. So I don't know how much better they're getting, and they may not be willing to tell any of us for now. They may well be building customized hardware that is optimized for doing this kind of factoring to see how high they can get. So that's state of the art on factoring, not going to be an issue in the near future. What else could we do? Simulating quantum systems. This is what the original motivation for quantum computing was. And it's still one of the earliest and best and most likely first uses. So if we take as an easy example to see why, let's take n of these 2-state particles, so like qubits, but they don't need to be qubits now. They could be in some material that we want to model. We have 2 to the n possible states that it could be in, right? It could be in a superposition of all of them. So you're trying to keep track of 2 to the n possible states in order to model it accurately. Classically, what that would require, 1 complex number per state, 2 to the n plus 1 times size of a double, say. So you get a terabyte holding n equals 36. And for each additional particle, you double that memory requirement. And that's before you do the time evolution on it, which requires matrices that are 2 to the n by 2 to the n. There are compression methods that can squeeze a little more. And some of this, in fact, was developed to model that verification I talked about for the useless sampling task that was claiming quantum supremacy. But if you're going up towards about 100 qubits, you're well beyond exascale. And you're into interesting territory as far as computational devices are concerned. And that's a lot less than we were talking about for factoring here to be interesting. Of course, if you don't need to track all those superposition, larger classical simulations are possible, and lots of them are done all the time. Matrix product states, tensor networks, many different methods for this. But it remains that somewhere around between 30 and 60 or so qubits is the limits on the size of what you can reasonably do with classical computing if you need full generality. And if you don't need full generality, you're in a subspace of this size. So that size is the hard limit. and you need to push your quantum system so you only simulate it in a small piece of its state space that is this big, no matter how big your simulation is. So what are we going to build our quantum computer out of then? At the moment, there are lots and lots of candidates. It's still early days. So I want to tell you a little bit about this just to give the feel for how open the field is at the moment and how it's hard to predict where the winds are going to be. But there will be some very interesting hardware to play with now or very soon. So there's the circuit model that I explained a few slides ago. I'm not going to explain measurement-based. You trade more qubits for a simpler way to do the time evolution, basically. These are all these quantum annealing D-wave style computation ones. There's also analog equivalents. Boson sampling in some ways sits in there. And full quantum analog computing also is possible. Now, if you want to do quantum simulation, you may find yourself wanting to use techniques from all of these ways of doing computing. Depends what kind of simulation you want to do. So what we're going to build our quantum bits from, there are many choices still. So I've mentioned the superconducting qubits that Google and IBM have been building. One of the newer contenders is Rydberg states in an atom cloud. So you take an atom and you excite the electron to very high quantum numbers here. So it becomes very big, essentially. And that makes it easy to do the 2-qubit gates. You can make a defect in diamond. So if you carbon atom, you replace one with a nitrogen, you end up with dangling bonds and missing atoms here. And the excitations of these make very nice qubits that even work at room temperature. You can put atoms in optical lattices, which is kind of making an egg box with lasers and trapping atoms in the wells. Light also comes in single units, but it always moves. So you have to keep it around long enough to compute with. And there's two ways that you can do this, essentially. One way is to trap it. If you put it between two mirrors, it bounces around like having a standing wave. And then you can interact it with an atom in this little cavity here. And then you can get something that there's a 0, 1 and a 1, 0 between the atom and the photon, or the atom excited and no photon. Or you can send light through waveguides which have features that behave like quantum gates. And I'm showing you this because this came out of Bristol in the UK and has become one of the companies with making some of the most extravagant promises and with a lot of venture capital. And their entire technology is based on building on something like this. So this was online for a while. You could play with it on the internet, but I don't think it is anymore. So who is building these quantum computers? Clearly universities and research centers, but there are also now many companies, and notably the ones that you'll be hearing about, IBM, Yorktown Heights, US, but also in Ruchlikon near Zurich. They have quantum computers there. They're doing serious research on. Google, mainly in Santa Barbara in the US. D-Wave Inc. is in Canada, but also the US and other countries now. Rigetti is a San Francisco startup, and there's also a UK arm of it now. IonQ in Maryland. So all of those ones are doing superconducting qubits, much like this IBM 7-qubit chip one here. So 7 qubits on this. So now they're making chips with 60 or more, but you can see the qubits. These little things are the qubits here. a few of you in the audience may be old enough to remember when you could see bits, when a classical bit in memory, core memory, was large enough to see with the naked eye. So that is the equivalent engineering level of quantum computing currently. We're just going beyond down the scales to below what you can see with the naked eye. These bigger things here are resonators because it's microwave frequent energy scale, and microwaves are centimeter sized. So if you want a resonator for a microwave, you have to wrap it up to fit it on a chip. So IonQ, as the name suggests, is ions in a trap. So they currently supply, they've very recently announced a 32 qubit low noise in device in a 19-inch rack, designed deliberately so that you can slot it into a server room and hook it up to your HPC and run the two together. And there's PsiQuantum in Palo Alto, who are building the photonic versions, but I don't believe they have anything you can play with yet, whereas these ones do. So D-Wave, which I've said less about, has 5,000 qubits now. They're noisy and they're not as powerful, which I'll explain on the next slide. But I just want to say one more thing about IonQ. They're saying their next version will have 64 or 60 or something like that low noise qubits. However, to do that inside the box, they will actually have about 1,000 ions and they'll be running error correction. So you'll see a box with 60 odd qubits, much better quality than these, but under the hood, they'll actually have a lot more physical ions doing the work to make those logical qubits. Now then, D-Wave, how does that technology work and how is it different? So if you want to do programming differently from the gate model, you have to encode your program somehow. So this is how it works for optimization problems, encoding into Hamiltonians that are then applied continuously in time. So we take our basis states again. So this is our zeros and ones. And we can make a superposition of all those basis states again. And I've just written this in more complicated language, but it's essentially that 0 to 7 again, but for n. And we encode the problem into our Hamiltonian such that the solution is the lowest energy state. So it's the ground state. And then you want to take your system and cool it into the ground state with that Hamiltonian applied. So if you want to find a Mark state, you just make the Mark state one lower energy than the rest of it. And that's kind of a trivial example because obviously you have to know the answer to set that Hamiltonian up. But what you want to think about it is the optimization problems are applying constraints. So if you have a constraint where you have 3 qubits, but exactly one of them must be 1, then you can put a term in your Hamiltonian that looks like this. And that will, for the lowest energy state, ensure that only one of these bits is flipped. And then you need something to drive the bit flip so that you can actually change the state and find the ground state. And so this is a Pauli sigma Z operator that sets up the energies being different for spin up and spin down, or 0 and 1. And this is a bit flip, so it's just a NOT operator. So it lets you flip bits and try to look to see, try and make sure the energy goes down as you do it. So here's a cartoon of how that can work better for quantum than for classical. So it's like simulated annealing, where you have lots of hopping around and you lower the temperature as you go so that you tend to settle into the minima. And that's fine if you have a nice broad one, and the quantum state will get stuck in that too. But if you have a lot of similar, small, narrow minima like this, you're likely to get stuck classically in one of the ones that is not the true minimum. But what the quantum state can do is tunnel. So it can get between these minima without having to jump over the top, so long as they're relatively close together. So that's the extra piece of quantum oomph that you get out of this model. So there are, of course, some elephants in the room, things I haven't discussed. Quantum error correction, I've mentioned briefly, but essentially it's not user level. As I implied, what you'll get from a programming point of view is a box with logical qubits available. It's resource intensive though, so the advances may not come as fast as you think as the number of physical qubits increase. Quantum verification, it's non-trivial, but we know how to do it without needing exascale computing. So you don't have to worry that you won't know your quantum computation is correct once it gets large enough not to be simulatable on classical computers. We know how to handle this. Integrating quantum with HPC, well, there's all the problems you'd think of, timescales. Do the qubits run at the same clock speed as the classical bits? No, almost certainly. They can be orders of magnitude different. Data formats, data type conversion. And I haven't said much about what I do. So in the last few seconds that I have, I will tell you very briefly something that I do. So one of the things is these science of computing, like the diagram I gave. And I also work on quantum annealing algorithms. And one of the vehicles, so that logo that sat here without comment up to this point, is a collaborative computational project for quantum computing that was funded in 2019 in the UK, which is networking between quantum computing community and computational scientists to develop algorithms, the all-important algorithms that will let quantum computers be useful. And so one of the ones we're working on currently is to interpret the diffractions patterns that you get from crystallography experiments where you have the amplitudes but not the phases. So it becomes a big optimization problem to try to assign consistent phases and back out the structure. And we want to see if we can do this better with a quantum annealer. So I will leave you with that slide, and I'm very happy to take questions. Thank you for listening.
Okay, thank you very much, Viv, for this very nice talk. So, so far I didn't get question on the chat. I want to say that you will stay online about 20 minutes after your talk, so you can still respond. So maybe
sure, very happy to.
Okay, maybe I have a few questions myself that I can ask. So in a classical computer, you have this image of memory and CPU. It's not clear to me if it's the same picture I should have. Really, there's a memory and a CPU unit, or everything is mixed?
There are models that can be built that way, but not all of them are. So with ions in particular, you can think of the trapped ions as being on a chip where they're shuffled around. And so there are some places they're stored, like memory, and other places they're in an interaction center for doing the gates, like a CPU. And there are also models where you copy the quantum state from a memory into a different kind of physical qubit, which is better for doing the gates, like the CPU. So that it's possible, but it's not required. So there are other models that look completely different from that and don't have that concept of memory and CPU. You take all your qubits and you compute with all of them at once, basically.
Okay. So now I have a question on the chat saying quantum verification, non-trivial process. Can you explain a little bit more?
Okay, so for quantum verification, for classical verification, one of the assumptions you make is that you can copy classical data, no problem, right? You can't do that with quantum states. unless you know what the quantum state is, you can't make a copy of it. So that makes it a little harder to figure out how to run standard verification techniques on it. But there's a whole lot of work on how to do that. So mostly it involves repeating computations. So if you have a gate sequence, so a program for a quantum computation, so in the simplest model, it's got a pattern to it, right? You've got 2 qubit and single qubit gates, and there's a certain amount of shuffling you can do to put it into a standard form. What you can then do is take another set of gates that matches that standard form, but is chosen such that the output is known. So it's like applying a very complicated identity to it. So then what you do on your quantum hardware is you run a whole bunch of versions of ones where you know the output, and in there somewhere you put the one where you don't know the output. That's your real computation. And the statistics of that output, so you can see how many of the ones where you do know the answer come out correct. And if maybe 99% of them, there's only like one error, that gives you a bound on how likely it is that the one that's the real computation is correct. So that's known as quantum accreditation. It was developed by Animesh Datta at Warwick University in the UK. And there's a whole bunch of other techniques that have been developed out of a project at Sandia Labs led by Robin Bloom-Cahoot, quite a big National Science Foundation funded program there. So I've only told you very briefly one way of doing it, but it's important that you don't require more qubits to do your verification if possible, because you want to use as many as possible to do your computation at this stage. We don't have spare qubits that we can afford to just set aside and use for something like verification.
Okay, thank you. Maybe a last question from me about programming language. What do you think we should expect? Because I don't think every scientist should be expert in quantum computing or quantum.
Yes, so there are more quantum software startups than there are hardware, and quite many of them are developing quantum operating systems in the hope they'll be the next Microsoft. The one issue with this is the assumption that the gate model will eventually dominate. And I'm not sure we're at a stage of computing we can guarantee that. But whatever, most quantum computers currently have a Python interface. And libraries are beginning to be built up for each of the types of hardware, so that you don't need to know at a low level how to put the machine code level how to put the program together. So that's developing at the rate the hardware is, possibly a little faster, but of course you can't test how useful they are until the hardware catches up.
Mm-hmm. Okay, so now suddenly questions are flowing. So I guess we can't probably take, but there's a question about the energy cost of quantum computing compared to classical computing.
That's a hard one to definitively say anything about, because you have to take the particular quantum hardware and say, okay, what's its energy cost? And because you've got cryogenics involved, there's an overhead for cooling. So yeah, paradoxically, the energy it takes to cool something down to a low temperature is quite significant. So I don't, and I'm not an experimentalist, so I don't want to make pronouncements on that, but I don't think we should make assumptions either way about whether it's going to help with energy use or not. Possibly when we've got something reliable, 100 good qubits for doing quantum simulations on, if it would replace an exascale setup, maybe, but much more likely, it's going to go alongside the exascale, and you'll end up using just as much energy, but get more computing out of it. But I don't think we're going to end up reducing power consumption. I think we're going to get more computing out of the same or more.
Okay, so maybe I just give you a last question from the chat, and then we will close the session. So it's about the fact that quantum computing is useful to simulate quantum physics, I guess. But the question is, how far is it from other application, like, I don't know, in chemistry or other field?
So simulating chemistry is, of course, quantum physics for, and it's one of the front runners in that people are working very hard on that. And it's one of the ones where they're combining it with machine learning. So they're doing a quantum version of machine learning to get some traction on quantum chemistry. For other applications, so the quantum annealing is all classical problems. That's universal for classical problems, but not for quantum in its current incarnation. And there are lots of algorithms for things like solving differential equations, which again are just as useful in a classical setting. But a lot of this is going to come from actually trying to use it and saying, well, where are the bottlenecks in classical codes that we really want to try and find something that will improve them? You know, what's holding back our science because we can't do this particular piece of computation better? And then algorithms are creative. We'll find them when there's a real drive to go looking for them, and unless we end up with a no-go proof, the chances are we'll discover something that is interesting and useful in that space.
Okay, thank you very much. That was a very nice discussion and a very good opening of the PASC conference. So I thank you a lot, Viv, for this. So I will close this morning session with this. And so this afternoon we have a paper session, then we have a mini symposium session, and we have the interdisciplinary dialogue where, again, it's plenary, and that's where we will meet you again. So I wish you a good appetite, a good sleep, or whatever, depending on your time zone, and hopefully see you later.